In continuation of my last lecture, collision number and mean free path, I have given you one problem to do at home. I hope you all can do this problem, very easy problem. Still then, I like to give an interpretation of this problem in different ways. Say, for oxygen gas at 25 degrees centigrade and 1 atmosphere pressure, they estimate the number of collisions made by a single oxygen molecule in 1 second time. Also find the mean free path of this oxygen gas given the bond distance of oxygen molecule equal to 1.2 angstrom. So this is the problem. We have to calculate this first Z1 and then lambda. And this Z1 is given by the formula root over 2 pi sigma square C bar n dash. Sigma is the collision diameter and C bar is the average speed of the molecules and n dash the number density of the molecules, means number of oxygen molecules per unit volume of this gas at this temperature and at this temperature and at this pressure. So C bar we can calculate by this way, root over 8 RT by pi m, and n dash already formulated, P pressure, Avogadro number divided by molar gas constant and temperature. So m is the molar mass, R the molar gas constant, T the temperature. So this is given, all these formula are given. So now calculate. Most trouble to calculate this problem is the sigma, value of sigma. The value of sigma has not been given. Instead, they have given the bond distance. This is the bond distance of one oxygen molecule. This is the bond distance of another oxygen molecule. So this and the sigma, the collision diameter from this to this one. This is the distance between the two centers, between the centers of two oxygen molecules. So I have explained in my last class, this is a half bond distance, this is 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 half bond distance. So 1, 2, 3, 4 from here to here. 4 half bond distance means 2 bond distance, 2 into bond distance, 4 into half bond distance means 2 into bond distance equal to 2, sigma equal to 2 into 1.2 angstrom equal to 2.4 angstrom. So all these terms are given. Now let us calculate this problem. First we calculate this C bar. C bar equal to root over of 8 RT by pi m. This is equal to root over of 8 into 3, 8 into 8.31 R mole inverse, Kelvin inverse, and temperature 25 degrees centigrade means 298 Kelvin, and divided by this pi equal to 3.14 into molar mass for oxygen is 32 gram mole inverse. So all the values are given. So Kelvin inverse, Kelvin will cancel, mole inverse cancel, and this arc root over arc per gram will give you the centimeter per second, unit of the speed. So this value this value, if we do this calculations, then it will be 4.44 into 10 to the power 4 centimeter per second. So this is a very high velocity of this oxygen at this room temperature pressure almost, and you can see this will be equal to 0.445 meter per second. Kilometer per second. 10 to the power 2 meter and 10 to the power again 3, then kilometer. So it will be 0.004 kilometer per second. This is a very large velocity. Say suppose this is, I can give you one illustration. Say this is about 0.5 kilometer per second. Means 1 second time this one oxygen molecule can travel 0.5 kilometer, almost half kilometer. Say from here, it is Bankura. This is Bankura, and suppose it is Kolkata. And suppose this distance is about 300 kilometer. So the time required for this oxygen molecules to start from Bankura to Kolkata, it requires the 600 second means 10 minutes. 10 minutes means within 10 minutes the oxygen molecule can move from Bankura to Kolkata. If this molecule, however, this more time will be required on the way, the oxygen will make collisions with other molecules and the tree, building, etc. So time will be required very to large than this one. So this is a very large velocity, you say. So I can write here this one C bar is equal to 4.44 into 10 to the power 4 centimeter per second. Now we calculate the value of now we calculate the value of N dash. N dash means the number of oxygen molecules per unit volume of this oxygen gas at this temperature pressure. So N dash equal to E Avogadro number and divided by R into T. So we can put here 1 atmosphere and Avogadro number 6.023 into 10 to the power 23 molecules per mole and divided by R. If we like to calculate the number of molecules per cc, then R to be given the value cc atmosphere mole inverse Kelvin inverse. So this value of R will be 82 cc means centimeter cube and mole inverse Kelvin and atmosphere and mole inverse Kelvin inverse into temperature 298 Kelvin. So here Kelvin inverse Kelvin will cancel, mole inverse cancel, and the atmosphere cancel, and this will give you the value. This will give you the value 2.465 into 10 to the power 19 molecules per cc. Molecules per cc. So this number, this you just consider in 1 cc gas, 1 cc gas, 1 centimeter length, 1 centimeter breadth, 1 centimeter height. In 1 cc gas, this large number, almost astronomical figure, this number of molecules are occupied. So this is also very high. So here also N dash we can write 2.465 into 10 to the power 19 molecules per cc. So these values already I have calculated. Now the value of the Z1, number of collisions made by single oxygen molecule in 1 second time, and this one equal to root over 2 pi sigma square C bar N dash equal to root over 2 into 3.14, and sigma here it is 2.4, means 2.4 into 10 to the power minus 8 centimeters square into this C bar equal to 4.44 into 10 to the power 4 centimeter second inverse into this N dash equal to 2.465 into 10 to the power 19 molecules and mole inverse. So this value of Z1 equal to, you can see the centimeter, and here centimeter square cancel, and here it is this one molecules and centimeter inverse 3, and this centimeter will be cancelled. Centimeter square, centimeter cube, here centimeter minus 3, so centimeter will be totally cancelled. And this and this will give you the value. This will give you the value equal to Z1 2.8 into 10 to the power 9 here molecules and second inverse. So this is the number of molecules, and this number is very high. You can show it is 280 crore. Molecules in crore of molecules per second. Means this one oxygen molecule in 1 second time it will collide with other molecules, other 280 crore of molecules. So this molecule, this number is very high. So you can consider how many collisions are there for a molecule in 1 second time. So this one also you see the in each collision the velocity, directions and magnitude of this velocity of molecules are also changed. Now next one we can calculate the value of, so this one so Z1 we can write 2.8 into 10 to the power 9 second inverse. Or you can call the 280 crore collisions are being made by a single molecule of oxygen in 1 second time at this temperature and pressure. Temperature is 25 degrees centigrade and pressure is 1 atmosphere. So now we calculate the value of lambda. Lambda means mean free path, and mean free path we have already shown you that it is the distance between two successive collisions of a molecule. Say molecule here it is here one collision, here it starts, and one collision, and so this is the distance. Moved by 1 second time, and this is number of collisions 1, 2, 3, 4, 5. So this one will give you the C bar, average speed of the oxygen molecule per unit time per second, and divided by Z1, the number of collisions made by one oxygen molecule in unit time. Let's say here in 1 second time. So if we put here, this is 4.44 into 10 to the power 4 centimeter second inverse, and divided by Z1 equal to 2.8 into 10 to the power 9 second inverse. So you can see this value lambda value will be coming up 1.6 equal to 1.6 into 10 to the power minus 5. 1.6 into 10 to the power minus 5 centimeter. Or you can say, if you do it in angstrom unit, then it is to be multiplied by 10 to the power 3 and divided by 10 to the power 3. So this will give you 1600 angstrom, the value of lambda. So lambda is equal to 1.6 into 10 to the power minus 5 centimeter, or you can say the 1600 angstrom. 10 to the power minus 8 centimeter equal to 1 angstrom. Now we can see, say, what will be the average time? What will be the average time for oxygen molecule for two successive collisions? Say average time. Say here and here, here. So this is how much time from this successive collisions? How much on an average? How much time will be the interval between two successive collisions? So this one, this T, average time for two successive collisions. Of one oxygen molecule. And this T average equal to time, how much time required for a molecule to get another collision, or what will be the time gap between two successive collisions. And this could be done, say Z1, you see Z1 is the number of collisions occurring for one oxygen molecule in 1 second time. So for one collision, the time required 1 by Z. So this will be the 1 by Z1. This is the average time required. Z1 collisions are made by one oxygen molecule in 1 second time. So for one collision, for one successive collision, the time required 1 second by Z1. So this will be the 1 second. So this is equal to 1 second, and Z1 equal to 2.2. Z1 equal to 2.8 into 10 to the power 9 second inverse. This one unit time. So this one will give you 1 by Z1, 1 by Z1 equal to 4 into 10 to the power minus 10. It is equal to 4 into 10 to the power minus 10 second. 10 to the power 4 into 10 to the power minus 10 second. So if we express it in, say it is picometer, by picosecond, 10 to the power minus 9 second is equal to 1 nanosecond. 10 to the power minus 12 second equal to 1 picosecond. 10 to the power minus 15 second equal to 1 femtosecond. So this value, say multiply by the here 10 to the power divided by 10 to the power 2, and this will be equal to 400. This will be equal to 400 picosecond. So time is very, very small. Means the molecule is getting another collision within this short period of time, 400 picosecond. Say it could be written as 4 into 10 to the power minus 10 into 10 to the power minus 12 divided by 10 to the power minus 12. So this one will be equal, this will go upside, so 4 into 10 to the power 10 to the power 2. 10 to the power minus 2 will go upside, so it will be 10 to the power, it will be 100, 400 into 10 to the power minus 12 second. So this is picometer. Now different things, different interpretation you can do very easily with this two data, with these two values, Z1 and lambda. See, another thing is that, say if you see the dimension of this gas container. Say dimension of the gas container. Say it is equal to 1 centimeter. Say suppose here it is the gas, it is the container, and it is 1 centimeter. This is also 1 centimeter, 1 centimeter each. So the we like to calculate how many collisions the molecule will make from coming from this one to this one, from this one to this one. Whenever this molecule is going from here to here, how many intermolecular collisions one molecule of oxygen will suffer. So this one say number of collisions made by a single molecule of oxygen for traveling one centimeter distance. How many collisions will be there? So this number of collisions made by the molecule in before reaching this wall will be equal to 1 centimeter, and the mean frequency means 1.6 into 10 to the power minus 5. That means 1.6 into 10 to the power minus 5 is the distance by the molecule to get this next collision with other molecules. So from here to here 1 centimeter. So from this side to this side, whenever this molecule will go to reach this wall, how many collisions suffered by one oxygen molecule with other oxygen molecules. So this will be 1 centimeter, and this one is also 1.6 into the minus 5 centimeter. So this will give you 6.25 into 10 to the power 6.25 into 10 to the power 4. Or you can write 6 to 5 and 9. Means from 1 centimeter length of this two wall. So this molecule when moves from this one to this wall, the molecule will suffer 62,500 collisions with other oxygen molecules at this temperature pressure. Next, I like to see. So before going to this wall collision, before going to this wall collision by oxygen molecule, it suffered so many collisions with themselves. So this is very large. And next one, I have shown you that lambda equal to constant into P by P in my last class. With the rise in temperature at constant pressure, lambda will increase. But whenever the temperature is fixed, pressure is increased, lambda will decrease. If we lower down this pressure, this is kept constant. If we lower down the pressure, then lambda will also increase. With the lowering of pressure, the mean free path will increase. Means large distance it can move without suffering any collision. So suppose in a good vacuum, in a good vacuum, say pressure is 10 to the power minus 9 centimeter, 10 to the power minus 9 atmosphere. This is taken almost vacuum, good vacuum. It would not be made. Whatever the exhaust pressure you can apply, exhaust pump you can apply to reduce this pressure 0. So this is a good vacuum. So now I like to calculate what will be the mean free path whenever the pressure is this one at this given temperature of 25 degrees centigrade. Then the temperature is fixed at lambda P inversely proportional to lambda 1 P1 equal to lambda 2 and P2. So lambda 2, which is the mean free path at this pressure, this one, it will give you according to the boil, like this Boyle's law pressure value. Here this P2 and here P1 and lambda 1. So P1 is 1 atmosphere and lambda 1 we found 1.6 into 10 to the power minus 5 centimeter and divided by here P2 equal to 10 to the power minus 9. So this is equal to atmosphere. So atmosphere cancels. So this will give you 1.6 into 10 to the power 4 centimeter. 1.4 into 10 to the power 4 centimeter. Or you can say it is almost equal to 1.6 meter, 1.160 and meter, or it is about to 0.1 mile. So this mean free path is drastically large and 160 meter if the length will be the container, then this molecule, instead of colliding with themselves, it will collide the wall of the container. Since wall of the container is lambda 2, the distance between the two collisions is very large. Naturally, this molecule, instead of undergoing the intermolecular collisions, they will collide the wall more frequently. So this is all about interpretation of this problem, and after this we shall discuss the frequency of intermolecular collisions with like molecules and with unlike molecules.